The illumination system that we've been building so far, it's pretty good. At least 16 shades of digitally controlled constant current illumination. I'm very happy with it, but if you've been following along, I tend to not get satisfied too easily. For example, the rotary controlled version of it, really nice, really smooth. I love it. The button version though, could use some improvements. You gotta hold the button down to increase or decrease the intensity and hold it to go the other way around. What I would really like is a way to just tap the button and have it go right to the intensity that I want, and tap another button to have it go off. Better yet, there should only be one button. The other issue that I have with our circuitry is that it's a lot of it. I mean, I'm so proud about the fact that we were able to design and build this using first principles and some basic logic circuitry. But look how many components it takes to actually do anything. You know how long it takes to put these things together? I build these things by hand, and I'm not complaining. I enjoy putting these things together by hand, but it does take an awful lot of time. And if we wanted to make this even more complex or add some more features to it, well, it just means that we're gonna have to add more components, and it takes more time to build. And oh yeah, it's gonna take up more space than this. Aren't electronics supposed to be small after all? We need an upgrade. We want to have better control over our electronics. We need to improve our flexibility. We want the thing to take up less space, and we want to use less parts. Well, for that, we need a microcontroller. And this is the one I'm specifically talking about, the Microchip PIC16f152 series. Now there's lots of microcontrollers out there to choose out of. Some of them are super fancy, really expensive, and have all sorts of bells and whistles. The one that we've chosen is probably the opposite of all of that. And it's been around quite a long time. Wow, yeah. That's pretty old. But hey, things don't have to be new to be great. And honestly, even though these things are pretty old and relatively simple, they will do exactly what we need, and I love the way they work. And this datasheet describes how they work really well. By the way, yeah, it is a very big datasheet. But don't let that scare you. I'm going to use the next set of videos to hopefully ease us into this so we can get acquainted with how these PIC microcontrollers work and why they're so useful. The particular one that we'll be using is this one right over here, the 15223. It's a chip with 14 pins. There are some smaller ones and some larger ones. And other than the physical size, there are some other differences, like the size of the flash memory and some capabilities that they may or may not have. But for the most part, they work pretty much the same way. Now, if you're going to be following along on your own with your own device as we go through the next set of videos, fair warning. There is an absolute enormous selection of PIC devices available on the market. Yeah, and the only one that I've ever used is the one that we're working with now. So it's a good chance that you probably have a different one, and I'm hoping the differences aren't that big. So you might want to keep this data sheet handy. All 400 and some odd pages of it. Let's get started with the basics and get this thing wired up. So in the datasheet, there is a diagram that goes over the basic connections that are necessary. Now we are going to expand a little bit on these connections, but let's examine what's in the datasheet. Just like most integrated circuits, we need a ground, which is right here with the VSS, and we need a power. Now interestingly, on this diagram, it doesn't explicitly define the power going to the VDD connection, but there is one. We'll get to it. And critically, it does highlight the capacitor that you need to connect between VDD and VSS. And it's recommended that we use a 0.1 microfarad capacitor. Now this other connection over here called not M clear is actually the reset pin. Under normal operation, the reset pin has to be held high. In order to reset the device, you drop it low and then release it. And it's this resistor over here that makes sure that that pin is held high. This capacitor over here ensures that that pin stays high even if there are some momentary drops. That capacitor is recommended to be 10 nanofarads. And this resistor R2 over here limits any current coming in or out of that pin. Now, if we do drop the voltage on that pin to ground, well, that would reset the device. So I'd like to add a little button onto that pin that will allow us to reset the device on demand. So here's a revised circuit diagram. This, of course, is our microcontroller. There is our 0.1 microfarad capacitor connecting the VDD and VSS. Here is that not M clear pin on this side over here. and you can see it's going out into the 220 ohm resistor that we have over here. Flipping back to our diagram, that R2 resistor is recommended to be anywhere between 100 and 470 ohms. I happen to have a 220, so that's what I'm using. And the other end of that resistor connects to this 10 kilo ohm resistor over here, which on the datasheet is that R1, and we can see R1 is recommended to be 10 kilo ohm. And on the other side of that is our 22 nanofarad capacitor going to ground. And yes, our datasheet suggests that we use a 10 nanofarad capacitor. I didn't have one, so I'm using the next best thing. And from that point, I have another 1 kilo ohm resistor going through this switch to ground. The reason I have a 1 kilo ohm resistor there is to limit the current that goes through that switch. Now you'll notice in the datasheet, the other end of R1 goes to VDD. Now we've got it going up to this thing called ICSP-SEL. That is the select line for our programmer. Now, I'm jumping ahead a little bit, but I want to wire this up to make sure that when it gets time to program this device, we want all of our connections to be there already. And this ICPS or ICSP-SEL line is the select line. Essentially, without getting too detailed right now, in order to program this device, we need to hold it in reset while the programming takes place, and then we release that reset. So by connecting this line to this ICSP select lead, I've given us the ability to use our programmer to control the reset of this device. And there's also two other leads over here called ICSP DAT or data and ICSP CLK or clock. Those are more programming pins that also have to go into our device. The datasheet does describe them a little bit lower down under in-circuit serial programming. That's what that ICSP stands for. Now, although it doesn't give us a diagram, it does tell us that a series resistor is recommended not to exceed 100 ohms. And there are two pins on the device where we can make those associated connections. The last one over here is ICSP ground, which doesn't actually connect to our device, but it does make sure that our power supply and our programmer are sharing the same ground. Jumping back to the datasheet and looking at the pin diagrams, we'll find out exactly where we need to connect them on our chip. Here's the 14-pin variant here. If you have the 8-pin variant, that's the one you're going to look for. And I think, yeah, here's the 20-pin variant down here. But we're using this one, so this is the one I'm going to focus on. And here's the data and clock pins. You can see them on pins 13 and 12. And here's the not M clear pin you can see on pin 4. VDD is pin 1 and VSS is pin 14. Let's take a look at the breadboard and see how we can wire this up. Here's our device already plugged into the breadboard. Here's the switch that I want to use for the reset. And this bit over here is simply the header that we're going to use later on to connect to our programmer. Let's assemble our components according to this diagram here. Excellent. We got the basics wired up, we have a reset button, and we have the header for our programming pins, which for now we've left empty because we haven't quite talked about how we're going to program this. See, I must admit, programming a device like a microcontroller can be quite complicated, and I've done the research and tried a few different variants. I also discovered this lovely document on the Microchip website, which goes into all the details about how to actually program this device. And yes, this document is way too deep in the weeds for us today, but I did go through it. I read it front to back because I had to. I created my own programmer for this PIC device. For my first go at it, I used this thing called an Arduino. I had one lying around and I was interested to learn about it, so I gave it a go. It worked. I was able to get it to program the PIC device, but I gotta admit, I struggled a little bit. I don't want to get into the details as to why, especially this early into our series. Suffice it to say, I needed an alternative. For my second kick at the can, I used a Raspberry Pi to program it. You've probably heard of a Raspberry Pi. I mean, basically it's a fully fledged computer, downscaled, to this size. This is actually the device that I was using to program this thing. It's a Raspberry Pi Zero, and what's neat about it, it has these GPIO, or general purpose I/O pins. These pins over here I could program to generate the signals needed to program the PIC device over there. I know that's a lot of programming, but it's kind of necessary to make this work. It worked just fine. I was able to do it, but honestly, what I really wanted to do is I wanted to program the microcontroller using my PC, the computer that I have in front of me, because it's just here, and so I like using it. But just like every desktop computer, it doesn't have these general purpose IOs. So although I can write the code to generate the signals, there was no way for me to get the signals out of the computer onto the device, until I discovered these guys. Ftdi for years has apparently been making these amazing devices that plug directly into a USB port and transform them into general purpose I/O. Here's one of them right here. Fantastic. There's a USB connection. It goes right into the computer, and I can write code to generate signals that I could put onto these general purpose I/O pins, which then can connect to my PIC device to program it. Now, all of that is wonderful, but in all of those instances, I still had to go figure out and interpret this craziness so I could write the code to program this device. Now, you may not be interested in doing that, so there is an easier way. On the Microchip website, I was able to find a link to programmers, debuggers, and emulators. And following that link led me to a place where you can actually buy a programmer for this particular device. I didn't purchase one of those because I wanted to go through the process so I can understand how to program this myself. But if you're not interested in going through the same process, you can certainly buy it. Now, like I said, I didn't get one, so I can't comment on its usability or how well it works. But based on what I've been reading online, tons of people are using it. So now that we got the hardware out of the way, let's talk about how this device actually works. In the datasheet, there's this wonderful block diagram. I want to focus for now just on the memory portion right here. There are basically two buckets of memory in this device. One of them is program memory and the other is data memory. The size of the program memory varies depending on the device that you're using. But essentially, it's just a place to store a list of instructions that the device will carry out. Now, the data memory is another bucket that holds a set of registers. Now, for this particular device, each one of these registers is 8 bits large, and there are lots of them. Going down in the datasheet a little bit, you'll actually find a memory map which lists all of the different data memory registers in the system. And yes, most of them are grayed out, which actually means they're unimplemented, but that's actually a little bit misleading because these columns are not to scale. Looking closely, you can see each and every one of these rows is a single 8-bit register, but then you got this block which says general purpose registers, and that's 80 rows right in there. And then there's another block of RAM down here, which is 16 addresses big. So just this bottom half here is 96 bytes big. And there's at least 3 of them, and depending on the device, you might have another 3 over here. And the vast majority of them are general purpose, meaning they're empty registers. But some of those registers are special. For example, there's these ones right here in Bank 0. Port A, B, and C, Tris A, B, and C, and Lat A, B, and C. Let's investigate these, shall we? You might have seen them before in this block diagram right over here under ports. See, those ports A, B, and C are windows to the outside world. When you put information onto those ports, appropriate pins on the device will either go high or low depending on the value that you put into the register. If you look at the pinout, you'll get a hint as to which ports show up. You can see here RA0 up until RA5. That's the first 6 bits of port A. You can also see RC0 to RC5. That's the first 6 bits of port C. You might notice that there's no port B. Well, not on this device. But if you scroll down to the 20-pin device, sure enough, you'll start seeing RB4, 5, 6, 7. So the availability of ports that allow access to the outside world will differ depending on which pin out or which specific model of microcontroller you're using. But to figure out how to use them, we need some more information. Luckily, the datasheet has this in droves. There is a whole chapter on input and output functionality called I/O ports in the datasheet. And while there's a whole lot of information here, let's just focus in on the basics. So it says here that the port registers read the levels on the pin of the device. What this actually means is the value in the port register will change depending on the voltage applied to the pins. The port is a mechanism for the device to read data from the outside world. The lat registers below it are actually the output latch. So when we put information onto the lat registers, then that information will show up on those pins as an output to the outside world. And the tris registers down here control the data direction. So that determines whether the port is an input or an output. If we take a closer look at the tris register, it shows all 8 bits, and it tells you that if the value is 1, then the output driver is disabled, meaning that that pin is an input. And if the value is 0, then the output driver is enabled and the pin is an output. Notice under reset, they're all labeled as 1. All of the pins are by default an input. If we wanted to make it an output, we have to change the value in these registers to 0. Which bit gets a 0 determines which pin becomes an input or an output. So although the register is 8 bits wide, on this particular device, only the first 6 bits of the C and A ports are made available. So now we know how to configure the pin as an input or an output. Let's take a closer look at the port register to understand how to operate in the input mode. And here's that 8-bit port register. And it tells you here that if the value is 1, then the port pin is high. If it's a 0, the port pin is low. And we can see here that on reset, the values are all X, which makes sense because we're reading those pins, not writing anything to them. But it also says here that the access is read-write, which means that we could read or write to those pins. So we already understand that we can read the pin, but why would we ever want to write to the pin? Well, in this important paragraph here, it actually tells you that writes to the port X are actually written to the corresponding lat register. So it's a minor detail, but based on proper convention, you should never be writing to a port. You should actually be writing to the latch, which helps differentiate between input and output activities on the same pin. Let's take a look at the latch register. And as you might expect, it looks an awful lot like the port register, except there really isn't any detail here. It basically just says whatever value you put here is the value that will show up on the pin. Okay, so now that we know a little bit about how some of these data registers operate, how do we actually do anything to them? Well, that's where the program memory comes in. We have to create instructions that get copied or programmed into the program memory, and then the device will sequentially go through those items in the program memory as instructions. And those instructions will then do things like put information into those registers or read information from those registers and process them. And in the datasheet, there's a chapter for instruction set summary, which lists all of the different instructions that this particular device has. Now, rather than starting off with some of these instructions, how about we start off with some pseudocode first? So the first action I want our program to do is to configure tris-C for output mode. Remember, by default on reset, all of the pins are set to input mode. So in order to set them to output mode, we have to write 0 to the tris register. And I'm deliberately choosing C because, based on our pin diagram, I only have access to A and C. And right now, some of the pins in A are used up by this not M clear and by our programming connections, but port C is wide open. So that's the one we're going to use. Now, once I configure tris-C for output, the next thing I want to do is clear the output on latch C. And we do that by writing zeros to the latch register. After I've written the 0, I'd like to invert the output latch C. So turn all the zeros to 1. And then I'd like to repeat the previous line, which is this one, invert output latch C, which would turn all the 1s to 0s. So the pseudocode for the program that we've just written here will basically flash all of the pins on output C on and off repeatedly. Now let's dive into the instruction set summary and take a look at what instructions we're going to need to make that happen. The first instruction we're going to use is this one here, CLRF. Scrolling up a little bit, I can understand what F refers to. It's the register file address. In other words, F points to a particular location in the data memory. And the particular location I'm interested in is right over here. There is tris_c, and we can see the address of tris_c is 014H. That's 014 in hexadecimal. Going back to our instruction set, we can see that clear has a certain code for that command. It's 00001 1FFF FFFF. So the file register of tris_c, which is 14H, needs to fit into these Fs over here. Now we can't simply take 14 as the address and write it into those Fs, because that address was given to us in hexadecimal, and these codes over here are given to us in binary. So, oh yeah, you're definitely going to have to brush up on your binary and hexadecimals. Wikipedia has some great references on binary numbers. I encourage you to read up on this if you're a little bit rusty. You're going to want to become an expert at binary and also hexadecimal. Honestly, it's not so bad. It's really logical to understand the difference between our normal base 10, which is numbers 0 to 9, and base 16, which is hexadecimal, and base 2, which is binary. I actually have this handy little calculator here which does those conversions for me. Get one, whether it's physical or digital, you're going to use it a lot. The other thing that you're going to want to brush up on is bitwise operations. Now, Wikipedia has a great source over here. There's a lot here. I think to start with, just understand the not, the and perhaps the or. The XOR is going to become handy, but not quite yet. You can save that for later. And the rest of this stuff is helpful, but ease into it slowly. So going back to our instruction set summary, let's adjust our pseudocode so we can insert the CLRF command into it. We'll type it in here. And then we need to include the address to the register that we intend to clear. And recall from the memory map, it's 014H. So we'll write in 0x0014. When writing code, that 0x lets humans understand that the 14 is a hexadecimal number. Now the next line of pseudocode also requires us to clear something. So let's insert CLRF. Now we have to find the address for the output latch. Our memory map says that latch C is 01AH. So let's pop that in over here. The next line says we have to invert the output latch. Going back to our instruction set summary, there is a command here called COMF, which delivers the complement of whatever is inside that F register. And the complement is the same as an invert or a not based on the bitwise operators we were just looking at. But you'll also notice something interesting here. This has a D. Scrolling up to what a D means, see, D here is a destination select. If D equals to 0, then the result of that instruction will be stored in W. Looking a little further up, we can see here that the W is the working register or the accumulator. We're not using the W just yet, so more on that a little bit later. What we really want is we want to store the result in file register F. In other words, we want the inversion to take place, and we want that inverted value to be put immediately back into latch C. So we're going to want to use 1 for the destination. So our pseudocode will look like this. It's going to use the same address as the latch C register, and then we have a comma 1. Indicating that that's where the result needs to be stored. And then our last pseudocode line says repeat previous line. There are a few ways we can do this. We're going to use the BRA or relative branch instruction. The relative branch instruction requires a K. Scrolling back up, what the K is a literal field constant data or label. So basically the relative branch instruction instructs the device to go forward or back K instructions. And in this case, we want it to go back 1 instruction. But we can't simply enter in BRA001 because that would instruct it to go forward by 1. If we want it to go backward by 1, we have to use this technique called 2's complement. This is another concept you should get comfortable with, and Wikipedia has a good article on it. Basically, 2's complement is a method to describe negative numbers without actually using a negative sign. So in our code, -1 is actually going to be written FFFE. Taking another peek at the instruction set, you'll see that the K constant for the relative branch instruction is only 9 bits long. So the maximum value that you can branch is 1FF. It can't go any bigger than that. So although we could leave this at FFFE, I find it to be a little bit more accurate to put in 1FE. You'll see later on that really it makes no difference. If you want to leave it at FFFE and you're happy with that, go right ahead and leave it like that. So if you're a little dazed by now about binary and hexadecimal, it does get easier, I promise, but I really think it's important to understand this foundational level of how microcontrollers work. Because in practice, there are higher level programming languages that you can use. Like you can use C to create the code that gets programmed onto these devices. But in order to do that, you need to have a compiler that compiles that C code into this machine code. Or you can do what I like to do and code directly in assembler, which is one step above the machine code. It's a lot more, I don't know, for me anyways, satisfying to understand how this device works. But if you're not of the ilk, you can go back to C at some point, or in the future, I should say. But for now, just stay with me because there's a little bit more that I think is important for us to understand before we can escape to some of the more higher level programming languages. So let's dig into this and keep working on our program a little bit, and hopefully things will come to light as we get deeper into it. So let's examine the first line in our code here, CLRF 0014. The datasheet shows the binary version of the CLRF instruction, 00001 1FFFFF. And as we just discovered, those Fs are where the binary representation of the target register goes into. So I've written it out onto this little sheet of paper here. Here's our CLRF command. Here is the binary representation, 00001 1000000, and it's divided up by the nibbles. So here's nibble 0. A nibble, by the way, is just half a byte or 4 bits. So here's the first nibble, second nibble, third nibble, and half of the fourth nibble, I guess. And then here's the hexadecimal translation. I find it convenient to be able to position the bits into nibbles because they very easily translate into hex. 0 becomes a 0, 1000 becomes 8, 0001 is 1, and 0 is 0. Easy. Below that, I've added the tris-C register. And the tris-Z register is only 8 bits, and you can see it here, 0001, which translates to 1, and 0100, which translates to 4. So there's our 4. These values are ORed together. But before writing out the result, let's look at our next line of code. It's the same thing. CLRF, there's the same bit string, 0180, but this one is applied to lat C. And so here we can see the 1A value in our binary representation. Keep going. The next line of code is COMF, and you can see the 900 hex value that this binary string translates to. And then there's the lat C, 001 1010, which is 1A, just like up here. But we also have this direction indicator. And finding COMF in the datasheet reveals that that D, or direction indicator, is indeed located right over here, which matches the position I put it in on this worksheet. And if you convert it to hex, you get 80. And of course, our last one over here, BRA, which is 3200 or 3200. And then there's an offset, the K value we talked about earlier, 1FE, and there's the binary representation. Let's write that out in detail in our pseudocode. Now let's perform the AND on the worksheet. The bitwise OR is very straightforward. Now that we have the hexadecimal results, let's enter them into our pseudocode. Those hex values that are written in black in our pseudocode are the actual instructions that need to get programmed into the device. But working with these numbers like that is painful at best. I mean, imagine writing lines and lines of code, which is just numbers, and then having to interpret them. I mean, it would be such a headache. Luckily for us, we can use our assembler to actually assemble those mnemonics into those codes for us, which means that in reality, we can certainly do something like this. You notice how the instruction commands were highlighted in blue? That's because the IDE I'm using, or the text editor I'm using, is interpreting the fact that these are assembly code instructions and it recognizes them. By the way, if you're using the same IDE that I am, you might want to go grab this extension called the PIC18 assembler syntax. It's not exactly the same as what we're using. We're on the PIC16, but it seems to work. The reason this works is that if we peek into the assembler code that I have here, don't worry about this code right now, we're not going to dive into it. I just want to show off the fact that there is a command dictionary in here, and those commands have associated opcodes, operand masks, and direction masks. And if you look through this, you'll find there's the CLRF command, and it translates to 0180. There is the COMF, or complement command, and it translates to 900. Down here you can also see the branch command, which translates to 3200. Which means we can use friendly names for our commands and rely on our assembler to translate those into the codes that our device actually needs to interpret. And then over here we can revert back to the register address that we had earlier, which is phenomenally easier to work with. And as an added bonus, the assembler I've written will also interpret that (1). That makes sure the result of this instruction gets put into the correct register. Taking another peek in our assembler code, you'll see that there's actually a list of register names here as well. Well, that makes things a whole lot easier, because now I can replace that hex number with the friendly register name. Now this is starting to look more like code that we can work with. But there's a little bit more housekeeping. In the memory organization chapter of the datasheet, it describes this thing called a reset vector, which is located at address 0, and an interrupt vector, which is located at address 4. The on-chip program memory actually starts at address 5. So we're not going to talk in detail about the interrupt vector yet. We're going to save that for a future episode. The reset vector, however, is important. Basically, what the reset vector says is that anytime the device is reset or started fresh, then the first line of code which it will issue is located at address 0000. So right at the front. But what's interesting is that the interrupt vector is at address 0004. So if we simply started adding code from 0 and went forward from there, one of those lines of code will overwrite that interrupt vector. For now, it wouldn't be a big deal because our interrupts are not enabled. Like I said, that's a future episode. And so our program would run along normally. However, at some point in the future, we are going to be using interrupts. And at that point, that interrupt vector is going to become relevant. So what we need to do right now is to ensure that we skip that interrupt vector. So we have to include another line in our code that says when we reset, in other words, once we reset back to 0, we need to go to the line of code that occurs immediately after the interrupt vector. In other words, we need to insert a line of code that says go to address 5. Just like that. So the first instruction says go to instruction address 5. But instruction address 5 appears to be this one over here, the branch instruction. And if we programmed our code like this, that's indeed what would happen. So we need to insert some information that organizes our code. And the org directive, I think that's what it's called, is used for that purpose. By inserting an org 0005, that tells the assembler that the next line of code is actually occurring at address 0005. So anything between the first address and address 0005 are empty. And it's good habit to start off the code with another org that starts at 0. It's also good habit to put in some comments and indent our code appropriately. Now, although the code will technically work as is, there's still a little bit more structure that we need to add to this. You recall how we were able to use friendly names for our instruction names and our register names? We can also use friendly names to go-to addresses, which means we can introduce labels like this, and then use those labels in place of go-to addresses. And then finally, we want to separate out our code from the little portion of the code that's going to be continually repeated. And I'll do that by assigning a label called main. We need to end the program with another directive called, yeah, you guessed it, end. Finally, this code is ready to assemble. So let's assemble it. Now bear in mind, the assembler that I'm using is our own creation. Like I said before, we're not going to get into the details of how it works right now, but you can see some of the outputs. You can see the friendly names and the encoded version of those lines as well. Those numbers should look familiar, because other than the first GOTO statement, the other 4 codes we came up with already. Here's one of the previous iterations of the pseudocode that we did, and look at those numbers, 194, 19A, 99A, 33FE, which match exactly to the encoded values in our assembler. Now the purpose of the assembler is to translate the friendly names into those encoded values, but it also needs to encode those values into a hex file. This is what the resulting hex file looks like. Now the next step is to process that hex file and generate the signals on our programmer so we can send those signals to our microcontroller and thus program it. Now, I hate to do this to you, but we're not going to do that today. We've already gone through a lot, but we've laid a very strong foundation of our understanding of how these microcontrollers work. Next time, on our next episode, we will go through the programming process and we will start editing the code to actually make something useful. See you then.